I would like to thank the organizers, and for me it's really a pleasure and an honor to give a talk at this conference. And also it's always nice to be back to Grenoble and the Institut Fourier. And so this is a Fano fourfold morning, so the talk is about still smooth, complex Fano fourfolds, but from a different perspective. So we will focus on Fano fourfolds with large Picard number. Let me start with some introduction. So let's take X a smooth Fano variety. So now it's well known since the 90s that there are finitely many families in each dimension. And they are classified up to dimension 3. So for curves, we only have P1. In dimension 2, we have the Pezzo surfaces. Which are P2, P1 cross P1. And the blow-ups of P2 in up to 8 general points. No. Okay, up to the del Pezzo of degree 1. Okay, and in dimension 3, we have 105 families. And the classification now, I would say, is 40 years old. And it was achieved first in the case of Picard number 1 by Iskowski and the Russian school, also building on the work of Fano. And then the case of Picard number bigger than 1 was classified by Mori and Mukai. Okay, and as I said, an important invariant that I want to focus on is the Picard number. But in fact, since X is Fano, by the exponential sequence and Kodaira vanishing, this is just equal to the second Betti number. So it's a topological invariant. It is constant in families, in smooth families. So it takes finitely many values in each dimension. And we see that for the Pezzo surfaces, the Picard number is at most 9, achieved for the del Pezzo of degree 1. And for Fano threefolds, we have a result by Moni and Mukai. From 86, that if we have a Fano threefold with Picard number at least 6, then X is a product of a del Pezzo surface with P1. Okay, so let me recall that the product of Fano varieties is again Fano, and conversely, when a Fano variety is a product, both factors are automatically Fano. So here S is automatically a del Pezzo surface. And also, since Fano varieties are simply connected by the Kunet formula, the Picard number of a product is the sum of the Picard numbers. So here we get that rho of S times P1 is the Picard number of S plus 1, which is the Picard number of P1. So it is at most 10. So as a consequence of this theorem, we get that for every Fano threefold, the Picard number is at most 10, and for rho between 6 and 10, we only have products. So this is how they ended their classification of Fano threefolds, so that starting from Picard number 6, it was done. OK, so I want to discuss an analog result in dimension 4. So if we have a Fano fourfold, if the Picard number is at least 12, then X again is a product of the Pezzo surfaces. Okay, and so similarly we get, since the Picard number of the product is the sum of the Picard numbers, so it's at most 18, 9 plus 9. As a consequence, we get that for every Fano fourfold, the Picard number of X is at most 18, and for ρ between 12 and 18, we only have products of surfaces. Okay? Yes, sorry.
Does the result include the Picard number equal to 12?
Yes, I will comment on this in a minute. Yes. Okay. And okay, let me say, so the first question is whether this condition is sharp. And in fact, we do not know, because all known examples of X, say, different from a product of surfaces, have at most a Picard number 9. Okay, so we do not know what happens in Picard numbers 10 and 11. And so I expect also for Picard number 11, there should be also only products of surfaces. In Picard number 10, I don't know. And yes, one aspect of this is that we have very few examples. Of Fano fourfolds, again, not products of surfaces, starting from Picard number 6. Okay, and okay, what do I mean by very few? I mean that in Picard number 6, we have 10 known families. 7 of which are toric. Okay, and in Picard numbers 7, 8, and 9, there is one known family in each row. Okay, so this is very few because it should be compared to the cases of Picard numbers like 1, 2, or 3, where we have hundreds of examples. Okay, and yes, it's a very interesting problem, I think, to try to construct examples in this range and to understand what happens in Picard numbers 10 and 11. And yes, and maybe in this range, it's even possible to get a classification. Okay. Okay, I want to explain what is this family of maximal Picard number that we know with Picard number 9, and then I will comment on this 12, on the case of Picard number equal to 12 in the theorem. So the family so in fact, it's the same construction that gives these 3 families. Okay, so you can do it with Picard number 7, 8, and 9. So we start from P4, and then we blow up 8 points. Okay, it's easy to see that this blow-up is not Fano, because if you look at the transform of one line through two of the blown-up points, it has intersection 1 with the canonical class. So minus k cannot be ample. But it's possible to do a birational transformation given by some flips or maybe anti-flips, depending on your terminology, and get x, which is smooth, and Fano. Okay. So this is a birational map, which is an isomorphism in codimension 1. This means that it is an isomorphism between two open subsets whose complements do not contain divisors. Okay. And in particular, it preserves the Picard number. So here, the Picard number of x is 9. Okay. And yes, so this construction is due to Mukai. And also we studied it in detail in a joint paper with Giulio Codogni and Andrea Fanelli a few years ago. I'm not sure about the year, but so I will not write it. Okay. And okay, I also want to say that there is an intermediate model here. So let's do this. So you can do only some of these flips, and you get an intermediate model which is still smooth, which is a P1 bundle. It's a P1 bundle onto Y, which is a blow-up of P3 in 7 points. Yes. Yes, and in fact, if you consider the blow-up map, and you consider here the projection from one of the points, from one of the points. Okay, so this is, I would rather not enter into details, but it's a very simple geometrical construction, because if you blow up the point from which you are projecting, you get a P1 bundle onto P3, and then you blow up the remaining 7 points, and also here you blow up the 7 images of those points, and you do these flips to resolve the map, and you can still get a P1 bundle, okay? And this is a partial modification, and then you have the full modification, which is Fano. Okay, so I wanted to highlight this because today I want to focus on Fano fourfolds. So in the explanation of the approach to the theorem above, I want to focus on the case of Fano fourfolds which have such a map. That I call a rational contraction onto a threefold, which means a rational map that factors as this map there, so some flips, or if you want, a birational map, which is an isomorphism in codimension 1, and then a contraction, which means that it is surjective, connected fibers, and Y is normal and projective. So this is just a rational contraction, and then I'm assuming that Y has dimension 3. Okay, maybe I can also add that if you start from a Fano fourfold and you do flips, you always stay smooth. This is very special of dimension 4, sorry. And so it's like here, all these models are smooth, and also here, this x tilde is smooth. And also, I can always choose the flips in such a way that f is k negative, which means that minus k x tilde is f ample. Because x is Fano, but x tilde will not be Fano anymore as soon as I do flips. But still, I can take f to be k negative, and this is better for many reasons. And on the other hand, I'm not assuming anything on the difference of the Picard numbers here. So this map does not need to be elementary. Okay? So y may be very singular, and there may be divisorial fibers, for instance, or divisors sent to curves. So I'm just saying that from this point of view, the map can be bad. All right. Why I chose to focus on this case? Because if you, in fact, the first version of the theorem above was with the rho strictly bigger than 12. And then there was an additional property for Picard number 12, which was if the Picard number is 12 and x is not a product of surfaces, then there exists a rational contraction onto a threefold. Okay, so this is, in fact, in the published paper. Okay, and so there is an additional step. So in a work in progress with Saverio Secchi, we went back to study this case, the case where x has a rational contraction onto a threefold, and x is not a product of surfaces. And a few years ago, I had the bound 12 on the Picard number. But in fact, we have an improvement. So this is, and it's a work in progress, but this part is written up and fine, I think. So if we have, so there is a second part, which is the real part in progress, and I will mention it later. If we have a Fano fourfold, with a rational contraction onto a threefold, and we need to assume that x is not a product of surfaces, because this clearly has even a regular contraction onto a threefold. Just take a conic bundle here and the identity here. Then the Picard number is at most 9. Okay, so you see that this, together with this, it rules out the possibility of Picard number 12, and then it improves the bound in the main theorem. Okay, and this is sharp because we have the example here of the Fano model of the blow-up of P4 in 8 points, which has a rational contraction onto a threefold. Okay, so 9 is sharp. Yes?
So from figure number 12, you showed, you know that you have a rational contraction on a threefold?
Yes.
11 and 10?
11 and 10, I don't know. I don't know. Right. So somehow this yes, maybe I will come back to this later. in the proof of the main theorem, there is a lot of case-by-case analysis that took years. And somehow this case of the rational contraction onto a threefold was crucial. And then in the following cases, somehow it, in the case of large Picard number close to the bound, in particular in Picard number 12, yes, in all cases that I got, I always got this rational contraction onto a threefold in different cases, okay? But for, and I don't know for Picard number 11, okay. Yes, also I want to say that the proof of this bound, in some cases, it gives a very precise description of X. So precise that we are trying, so this is the part which is more in progress. We are trying to use this description to actually construct new examples, okay? Because we have like a picture of X, and then we are trying to show from the other point of view that this is actually a Fano fourfold. And we think that we should be able to construct new examples with Picard number 7. But so far, we did not get new examples with Picard number 8 or 9. But yes, so far, this is still the only family that we know in Picard number 9. OK, are there questions? The bound for toric varieties is 8, is in arbitrary dimension twice the dimension, okay? And for Fano fourfolds, the maximal, so toric Fano fourfolds are classified by Batirev, and also they are classified, I think toric Fano fourfolds later were classified up to dimension like 8. So there is an algorithm that given the classification in some dimension gives the classification in the following dimension, but then it just becomes too many cases. And the bound on the Picard number in arbitrary dimension, it's a result that I got many years ago after my PhD thesis, but the proof is completely combinatorial. So I actually tried hard to give a geometric interpretation of the proof to try to generalize it to arbitrary Fanos, but I could not. And also for toric Fanos, let me say that for fourfolds, in Picard numbers 7 and 8, we only have products. So this is why, yes, we have examples only up to Picard number 6, the toric ones. I mean, non-products, because for Picard numbers 7 and 8, the toric ones are products. So maybe there are more examples, but we just don't know how to find them. So one of the reasons that we have so few examples in large rho is that typically you will not find these fourfolds as embedded varieties, but you need to do some birational construction, either flips or blow-ups, and this is hard to control. It's hard to control in large Picard number. So for instance, if you try to prove by hands that in this blow-up you can do flips and get a smooth Fano fourfold, you will understand quickly what you have to flip, but then to prove that you can do it, it's another story. And in order to prove this, it's an idea by Mukai to interpret X and this blow-up as moduli spaces of vector bundles, and then to use the variation of stability condition to control the birational geometry. Okay, so in the end, the birational map is very simple, but to prove that you can do it and get something Fano, I would say projective and Fano, is hard. And yes. Other questions? Okay, now I would like to give an idea of how the main theorem is proved, and then I will relate to this theorem, because in fact they convey to the same approach. Okay, let me see. No? Okay. So I want to split the main theorem as a consequence of two results. And the first one I will take as a black box, and I will comment more on the second one. But first I need to introduce some notation. So as usual, N1 of x is the vector space of 1 cycles in X with the real coefficients up to numerical equivalence. So this is the real vector space of dimension, the Picard number of X. And so if I consider D in X a prime divisor, I'm not assuming that D is smooth, just any prime divisor. And so I want to compare the N1 of D with the N1 of X. So we consider the inclusion. And this gives a linear map by N1 of D to N1 of X, which takes the class of a curve in D up to numerical equivalence in D, and sends it to the class of the same curve, but now up to numerical equivalence in X. And in general, this map does not need to be injective nor surjective. And I'm interested in the image. So this is a linear subspace of N1 of X spanned by classes of curves in D. Okay. Okay, so here is the first result. That I would like to take as a black box. So Fano fourfolds such that there exists a prime divisor D with so I want to consider the case where there is a divisor where this subspace has a small dimension with respect to N1 of X. Okay, so in particular, I'm assuming that the codimension is at least 3. Fano fourfolds such that this happens are classified. And in fact, either X is a product of surfaces, or the Picard number is 5 or 6. And in this case, there are 17 families. many of which are toric. Now I don't remember the number. And let me put some attribution here. So it's an old result of mine that under this assumption, either X is a product of surfaces or the Picard number is 5 or 6, but then the classification is much more recent. So the classification in the case of Picard number 5, it's in a joint paper with Eleonora Romano, another former PhD student of mine. And the classification in the case of Picard number 6 is joint with Romano and Secchi. Okay, so you see that from this we can assume that X, so we can assume that we are not in this case because this is well understood. And so we can assume that X has a property that we call property star, that for every prime divisor we have that the codimension of n1 of the X is at most 2. Okay, so this is the first part, and then I will just keep this blackboard. Okay, now the main theorem here follows from theorem 1 and theorem 2. That if we have a Fano fourfold with property star, then rho x is at most 11. Okay? So you see that together they give the main theorem, because either we are in this case and either we have this divisor where the codimension of n1 of the X is at least 3, and either X is a product or the Picard number is very low, or we can bound directly the Picard number. Okay? And okay, so let me say that so somehow this is one work, while this is the outcome of really many works. And you see that there is a change of point of view, because we don't want to show that our X is a product of surfaces, but we want to bound the Picard number of a Fano fourfold under suitable assumptions. And this is achieved by using birational geometry in the sense of minimal model program, and with a long case-by-case analysis. It's actually a lot of work. But this assumption is crucial for several reasons, mainly because it allows to reduce a lot this number of cases which come from birational geometry. Otherwise, it would be impossible, because in dimension 4, the possible divisorial contractions and the fiber type contractions that you have are too many. And so this is essential. Okay. So what I want to do now is to give an idea. So you see that somehow this theorem is one special case of this. And I want to give an idea of the proof of the bound on the Picard number in the case where X has a rational contraction onto a threefold. Okay. And I have to, maybe I will write here. So, of the strategy, I will not actually prove anything, but when X has a rational contraction onto a threefold. Okay. All right. Okay, that's good, and we keep our example there. So we have our Fano fourfold with property star. And the rational contraction onto a threefold. But maybe before starting this, I can ask if there are other questions before going on? No. Okay. Okay, so I want to make 2 reduction steps and then to actually work. So the first step, so we want to replace this rational contraction with another one which has better properties. So I will state it as a fact. So there exists a birational map from y prime to y, birational, with y prime q factorial. So this is the first important property, but there is another one, so such that, so the composition I'm going to x to y and then with the inverse to y prime. So I'm saying that this is still a rational contraction. But it has better properties. And when we take a resolution, so let's call this f prime. Okay, so I want to say that f prime has fibers of dimension at most 2. And the 2-dimensional fibers are isolated. Okay, and so this is much better, both this and the fact that the target is q factorial. Okay. So the proof of this is actually more or less a standard Mori dream spaces techniques. So it's not really dependent on the fact that we are Fano or in dimension 4. So it's like, for instance, in this example, suppose that you are originally considering the map from x to P3 instead of y, then this step will give you back the map from x to the blow-up of P3, okay? And also, in this case, the problem is that there are divisorial fibers if you go to x tilde through 2p3. And another example is that this y, in fact, is a weak Fano, so minus k is nef and big, and it has a small anticanonical map to a singular Fano threefold. So we may also consider this composition from x to the very singular Fano threefold. This has the right properties on the dimension of fibers, but the target is highly non-Q factorial. So again, this step will give us back this nice P1 bundle onto a smooth threefold. Okay? Okay, and then so we replace the original map with this one. So from now on, I will assume that y is q factorial, and that when I take a resolution, I have these properties. Okay. Okay. And now I want to, before going to the second step, I want to say a little bit about the properties. Okay. So in fact, now in this setting, we have a lot of good properties. So first of all, so f is k negative. As I said, I can choose the resolution in such a way that f is k negative and x tilde is smooth. Okay, and then y is locally factorial and canonical. Or it's better to say y has locally factorial, canonical, isolated singularities. Which are possible only at the images of the two-dimensional fibers. Only, possibly. At the images of two-dimensional fibers of F. So it's almost smooth, I would say, very mild singularities. And outside these two-dimensional fibers, F is a conic bundle. So this just means that every fiber is isomorphic to a plane conic. So we only have three possibilities, P1, the two P1s, and the double line. And also, I want to say that the possible two-dimensional fibers that can occur are classified. They were classified by Andreatta and Wisniewski and Cacci independently in the 90s. And there are not so many cases. And this is very useful to have a precise picture of what happens. OK. And now let's go to the second step. Okay. So, well, in our example, y is smooth. There are no two-dimensional fibers, and F is even a P1 bundle. So it's special. OK, now let's go to the second step, where we use property star. So far we have not used it. So I will state it again as a fact that assumption star implies that the difference of the Picard numbers of x and y is 1 or 2. Okay, so this is the elementary case, like in the example. So this reduces a lot the possibilities. And okay, so I will not prove it, but I will give an idea. So I say that outside the two-dimensional fibers, F is a conic bundle. So we can consider its discriminant divisor. So this is a divisor in Y that corresponds to singular conics, to singular fibers. Okay? And then we show that if the difference of the Picard numbers is large, the discriminant divisor has many connected components. Okay? And when you consider the pre-images in X tilde, you get many pairwise disjoint divisors. And then there is another technical point that you show that when you take the transforms of these divisors in X, they stay disjoint. And then this bunch of pairwise disjoint divisors allow to contradict this, because you use them to show that one of them will have the n1 of the X with codimension at least 3. So basically, I'm not saying the details, but this is really the idea. Use the conic bundle structure, the discriminant divisor, connected components, and to have many pairwise disjoint divisors. Of course, when the difference of the Picard numbers is at least 3. And then to go back in X, because we have assumption star in X, not in X tilde. And then use it to contradict this. So in the end, this is where we use, in an essential way, this assumption. Okay? Okay. Now the third step is to bound the Picard number of Y. Okay, because we want to bound rho x, but we know that the difference is at most 2, so we actually work on Y. And so we assume that rho x is at least 7. This is useful because together with assumption star that I just erased, it gives you many restrictions on the possible elementary divisorial contractions that can occur both on X and in X tilde. So it's very useful when you apply birational geometry explicitly, just to cut down cases. And then we show that Y is weak Fano, exactly like in the example. So minus ky is nef and big. Okay, and so exists a map from Y to Y naught, which is the blow up of R distinct smooth points and the Picard number of Y naught is 1 or 2. And then, in fact, here we have a lot of additional properties that I'm not telling you because otherwise it becomes very technical. And so you see that Y naught has the same singularities as Y because we are blowing up smooth points, so we don't touch the singularities. And Y naught is still weak Fano. Yes, but here I'm not being precise. This is up to flops. Sorry. So in order to get this map, you may need to do some birational modification of your Y. OK. So now I should say that a lot is known on singular Fano threefolds. A lot of people have been working in different settings. In particular, I should mention Prokhorov, and also the works by Janke, Petenel, and Radloff. And so here, in order to bound the Picard number of Y, we use the anti-canonical degree, because it must decrease by 8 at each blow up. Here, this is easy from the formula for the canonical class. And so it must stay positive. So the anti-canonical degree of Y is the anti-canonical degree of Y naught minus 8R. So 8R is strictly smaller than the anti-canonical degree of Y naught. And then we see that rho x is at most rho y plus 2, but this is equal to rho Y naught plus R plus 2, and this is at most R plus 4. Okay? So you see that if we have a bound on the anti-canonical degree of this Y naught, we bound R, and then with the bound on R, we bound the Picard number of X. Okay? So it's an explicit geometrical argument working on the base. Yes, and I forgot to say that this is exactly the picture that we get here. So here Y naught is P3, and we are blowing up 7 points. OK. Now there is a work by Prokhorov from 2005. Where he shows that in this setting, the anti-canonical degree of Y naught is at most 72. And so you see that we get right away that R is at most 8, and the Picard number of X is at most 12. So this was my original bound from a few years ago. At the time, nothing was known on the maximal Picard number of Fano fourfolds, and I thought that 12 was very good as a bound. But in fact, pushing more and working more, one can improve. Okay? And this is what we do now. So this can be refined. But of course, you have to consider different arguments depending on the cases. So I will just give a brief idea. So if f is elementary, we consider separately the cases where y naught has Picard number 1 or y naught has Picard number 2. So in this case, I use still the work by Prokhorov, because Prokhorov shows this for every y naught. So when the Picard number is 1, y naught is Fano, okay, because an Fn big in Picard number 1 will be ample. And here he only assumes Gorenstein Fano with canonical singularities. But in our case, we have much more. We know that y naught is locally factorial. So in fact, he classifies the two cases where you have equality here, and they are two weighted projective spaces. They are not locally factorial. And so we use again Prokhorov. And also another work by Kazemanov. In 2009. So together they classify the cases where the anticanonical degree in this setting is bigger than 64. So they are in the whole 4 cases, and they are not locally factorial. Okay, and so in the end, this implies that in our case, the anticanonical degree is at most 64, which is actually what happens for P3. So we know that we cannot do better because P3 actually happens. And so R is at most 7. And in this case, where the contraction is elementary and the Picard number of y naught is 1, we get that the maximal Picard number is 9. Okay? And so this is actually the case of the example. So in this case, we use an ad hoc argument that I will not enter it. An ad hoc argument to give a better bound on the anticanonical degree. And maybe I will just say a few words on the non-elementary case. So the non-elementary case, so the case where the difference of the Picard numbers is 2, is actually the most interesting because it's more restrictive. So to have this construction, it's like as you had one elementary case and then the blow-up of a surface. So it's a much more restrictive situation. And so this is a case where we have a much more detailed description. So not only we can prove the bound 9 on the Picard number, but we get this quite a good description of X. So this is a case where we are trying to convert this in a construction of examples. And this is the part which is in progress. So we still have to work on it. But as I said, we expect so far to get examples with Picard number 7. 8 and 9, we still don't know. Yes, OK. So this is what I wanted to tell about the fourfold case. Let me just finish with a comment on a possible direction in higher dimension. So of course, this case-by-case analysis, it's impossible to repeat it in higher dimension. So I think that the right direction to higher dimension is to understand better this condition star. Remember, the condition star was that for every d, the codimension of n1 of dx is at most 2. So when there is a divisor where the codimension is at least 3, we have a good understanding of the Fano also in a higher dimension. Okay? So what we should understand is what happens to X when there exists a D where the codimension is exactly 2. Okay, so what I mean is that I think that the right direction of research in higher dimension is to follow this approach and to understand what happens in this case, which is still not clear even in dimension 4, I would say, whether there is a structure theorem for X or something like that. And that's it. Thank you.